Here we reach the new part on the interaction term, and that is basically when we learn about how factors, different variables work together. And this is, of course, the whole thing is part of the factorial design, which is used in pharmaceutical formulations optimization. So the common question here is when there is interaction between different variables, and that the question is, what is this interaction? And sometimes this can be thought of as the hidden relationship between those variables. So basically that means the effect of one factor depends on the level of the other, and the whole or the total effect is more than the sum of the parts, or it could be less as well. It could be both ways, either it could be more or than the arithmetic total or sum of both, or the sometimes it could be negative as well. And what happens here, you cannot be detected by one factor at a time of the experiments. And we've seen this term before. We represented this by this term is A3 x1 x2, and you will see this commonly used just to indicate how those two they will interact. So the bottom line, whenever you see this, then you know this is interaction between both of them. They will affect the y. Y is the whatever is the dependent variable you're checking or measuring. And this is quite important because interaction is very important for understanding complex formulations or recipes. Okay, if we look at this animation, hopefully it will explain this interaction term clearer. What you can see here is x1 on the x-axis and the response y on the y-axis. So you have here two levels. Look at the blue line here. Um, -1, that means low x1 with low um, x2. And as it goes higher, look at the other side, still on the blue line, high x1, low x2. But we see it's modest increased, which is expected in y. So there is increase when x1 is low, and then you increase the amount of x1, then variable 1, then there'll be some increase. But notice the red line here. Red line is high in x2, so low. Look at the start on the left side of the red line, so low x1, and then goes higher. But you see the augmentation here. When you increase the value of x1 of x2 becomes higher and higher, there will be higher amount or higher y response, and that basically means there is an interaction, there is augmentation. If this doesn't happen, if there was no interaction, you will see that both are parallel because they will increase the same magnitude. But here there is divergence. Basically means you added or increased the amount of x2, and that's more or less just gone in the other direction, basically increase the y response much higher. Another way to understand this, maybe something we encounter on daily life. So when you make a cup of sugar or tea, so here you will basically the response is the taste. This is how you're gonna taste things or taste the cup you're making here. Again, the same thing here. Look at the blue line. Blue line is basically the low for x2. Okay, and then you move from low on the left side, go on the right. There is some increase in the response. Basically, you're adding more of the sugar. And imagine that on the high, on the red, is the coffee is stronger. Basically, you have more coffee. then the taste will be augmented because you have more of the coffee, so more of the X2 and more of the taste is becoming much more noticeable. So the flavor becomes sharper because of the interaction. So that's just basically that's what it is basically interaction, and that makes the effect more noticeable. So how do we read an interaction plot? And this is often referred to as the visual fingerprint on factor relationship. So x-axis is one factor when we've been talking about pharmaceutical formulation. Y-axis is the response, and in terms of tablets is the hardness of the tablet. And you have different or multiple lines which different levels of the second factors. And I just suggest you just look at the examples we gave earlier. If they are parallel, there is no interaction, as we mentioned. The effect is similar. There is no kind of impact of one on each other. And once they become non-parallel, that means there is some interaction going on. Look at those two parallel lines. Basically, you go from low to high. The blue is low for x2, and the red is high for x2, and the x1 is showing on the x-axis. Y response is on y, and there is no difference here. So you increase so basically there is no kind of impact. Uh, it's not always a positive effect. So sometimes you can have interaction, but it will be a negative interaction. And here 1 plus 1 equals 1.5. It's just really indicates, doesn't mean of course mathematically correct, but that means basically the interaction between them, it will have a negative impact on y, on the response. So basically the lines will come together, they will meet, um, and that means the effect is less than expected. And you will see that in the equation by looking at the value of A3, which means the A3 will be a negative value. Um, and to some extent, that means the factors cancel each other.